You just completed a lab exploring the relationship between colored matter and radiation. In this experiment, we used different colored pockets and we looked at how they were heated. We used light to heat the pockets. When the light energy got absorbed by the pockets, it made the particles move, and this is an energy transformation where light is transformed into thermal energy or heat. At the end of this experiment, we saw that the black pocket was much warmer than the other pockets. It was at a higher temperature and had a bigger temperature change. If we were to examine how the particles were moving in the black pocket compared to the others, we would see that the particles were moving much faster. The black pocket absorbed more light, which meant that there was more thermal energy there, so the particles were moving faster compared to the other pockets, which absorbed less light. There was less radiation happening, less thermal energy, and therefore less particle movement.
We've learned that each color has its own wavelength and frequency, and some colors like red carry less energy, while other colors like violet carry more. For the sake of explaining this next concept, I'm going to assign a value of a number to each color. Since red has the lowest energy, I'm going to give it a 1. Orange, 2, all the way down to violet, because we know that violet has the highest energy, so we're going to give that a value of 7, which means it has the most value for energy. Let's take a look at what happens when white light, or Roy G. Biv, strikes a black surface. We know that red, orange, yellow, green, blue, indigo, and violet are absorbed. We assigned a number to each wavelength, knowing that, that each wavelength has a value in terms of energy. If I add up all these numbers, they add up to a pretty high number of 28. What that means is black absorbs all wavelengths of light and turns it into a lot more thermal energy or heat. Let's compare black to the opposite color of white. When white light, or Roy G. Biv, strikes this surface, all the energy is reflected off of it, which means that no light is being absorbed. None of it is turning into thermal energy or heat, so this has a value of 0 compared to our color of black, which has a value of 28. Significantly different in the heat or thermal value. Let's take a look at what happens when light hits a red surface. So white light, Roy G. Biv, strikes the red surface, and it reflects the color red. That's how we know it's red. Red absorbs all colors but red, orange, yellow, green, blue, indigo, and violet. That adds up to, if we look at those numbers, that adds up to about 27. So red absorbs actually quite a lot of the radiation and turns it into quite a bit of thermal energy. It's actually pretty close to that number black. Compare blue to red. When white light, or Roy G. Biv, strikes the blue surface, blue is reflected. That's how we know it's blue. Blue absorbs all colors but blue. Red, orange, yellow, green, indigo, and violet. Those numbers, if I add them up, adds up to about 22. Blue actually reflects one of the higher energy wavelengths, which ends up resulting in a little bit less thermal energy or heat as compared to red, which actually reflects one of the lower energy colors and absorbs all the higher energy colors. So we know that red surfaces absorb higher value energy because they reflect the lowest energy and absorb the higher energy. So their particle movement or heat ends up moving a lot more as compared to a blue surface. Blue surfaces reflect a higher energy and absorb more lower energy colors, which results in less particle movement and less heat.
So with radiation, it's all about what light is absorbed. When higher energy light is absorbed, according to law of conservation of energy, that results in more thermal energy or heat. When less light energy is absorbed, less thermal energy is there, according to law of conservation of energy. So look at what's absorbed and what's reflected to help you determine what's going to become warmer.